this is about this is a presentation about our L1C models for you, the users, the customers, to understand why we've developed, why Oxus has developed this this line of models, and what are the problem at stakes. I'm going to present first. Let me see the purpose of this line of products. Then the components it's made of. How you could use the L1C, and last I will show an application example. Maybe I will wait for the other people to connect. Okay, yeah, it was good. So I will start by the voice from our users that we have the issues that we came across. Some users tell that they need yellow, so 561 nanometer laser source that they could be modulated at several megahertz. Unfortunately, most of the lasers at this wavelengths cannot be easily modulated inherently. All the people would say, I need to adjust the power of my excitation laser for Raman application. In this case, you need to have the emission wavelengths stable while you adjust the power, and in some cases this is not obvious to achieve. Or other users would need an isolated laser source at 1064 nanometer, or some would simply need to replace their helium-neon laser. All these needs are supposed to be met by the L1C platform. The purpose of the L1C platform is to propose an assembly of laser sources and additional components in order to meet the need that have been expressed in my previous slide. So and we turn this into a compact and efficient solution. So at the bottom of my sorry, getting my focus. Okay, so at the bottom of my slide, the user can choose its laser source. He can add an isolator or a power adjustment function. So they just need a slow variation of the power, or alternatively, fast modulator. They can have a single mode coupling into the fiber, or they could have also a free space output, obviously, and eventually Oxus can also provide some beam shaping optics, or for the multimode beams we can propose, multimode and beams, signals that have an important coherence length. Some issues can arise from the speckle effect, so we can also propose a mode scrambler or despeckler, something to suppress the contrast of the speckle effect. And I showed two possible paths, two possible choices, the red one and the green one, but any user can choose his own components. So I will describe the function of the L1C and what it is. It's composed of a laser source, then an optional optical isolator. Also, most of the time, the function that the user are interested in is the modulator. So we can either propose a custom optic modulator or a motorized power attenuator. Every time there is an optomechanical shutter to shut down the power. And the last option is the delivery into an optical fiber, or as I said, free space. So we can propose either a single mode fiber, a polarization maintaining single mode fiber, or a multi-mode fiber chosen fit to the wavelengths that is involved. So each model is defined against a customization basis with our sales team. So now I will go in further details concerning each of these components. So first the LCX and the LPX, which are our laser sources in the red, yellow region of the visible spectrum, and a few models are in the infrared. So these are diode pump solid state lasers based on a monolithic resonator, which is the core technology of Oxus, and they rely on the principle of intracality doubling for the visible lasers. The LPX is a longer version of the LCX, and it allows to accommodate higher power. It's also the model for the 640 nanometer lasers based on Presertime lasers. So all those models are a single longitudinal mode lasers emission. We also propose the LBX, which is another platform based on the integration of a laser diode, mainly in the red region, the 633 nanometer, and near infrared 785 or 830 nanometers. And these also are single longitudinal lasers. So once the laser source is chosen, you can go and select the isolator. Most of the standard isolator can be selected. You can even suggest a model to Oxus. Then I will go into describing the part concerning the power modulation. I explained there are two choices, what we call the motorized power attenuator, the MPA. This is it's an attenuator, so it's not designed to be fast. It's more cost efficient, so the response time, it will be a little less than 1 second. The contrast is improved by adding the electromechanical shutter. The other option that you have is to use the modulator, in which time in this case, the rise time is in the range of 100 nanoseconds, and it requires an additional controller, which we call the BTC AOM, to host the driver of the modulator. There again, the contrast on-off is limited. It's typically 45 decibels, and the shutter allows the user to improve this extinction ratio, so to have a full extinction when the set point is nil. As opposed to this, we can propose a power adjustment, but which is also cost efficient. But in this case, the emission wavelength is not constant over the full range of power adjustment, which is why this solution is not suited for application where a constant emission wavelength is required. I will, yes, now I've reached the part about the injection or the output. So the output can be obviously in free space, but most of the users prefer to inject the beam into single mode fiber or into a multi-mode fiber. So our system, based on Schefter and Kirchhoff coupler, exhibits a high injection ratio, for example, into a single mode or a polarization maintaining single mode fiber. We typically reach 75% of injection, whereas in a multi-mode fiber, using specific models, we can reach yes, typically 90% of injection ratio. So how does it work? Also, yes, I forgot to mention that even though this coupler is what we propose by standard from Schefter and Kirchhoff, we can also propose the optical coupler from Keyoptic, which is called kinematics, in order to be compatible with well, systems that only allow for the kinematic system. So how does it work? How does the Schefter and Kirchhoff coupler works? The coupler is this round cylinder. It has several screws to adjust the injection, which is something we do internally on the factory. And then the user, the optical fiber, which is embedded into a patch cable, and it's connected to the coupler at this place. The user is not expected to remove the optical fiber, but it is possible to do so. Yes, and there's a flange, adaptation flange between the end face of the front face of the L1C and the optical coupler. So once the injection is adjusted, normally the user shouldn't have to optimize it any longer. This is another system that we proposed. It's called a repositionable fiber coupler, and it is meant to remove the whole coupler without having to remove the fiber. So we see you have an extra flange over the optical coupler compared to the previous slide. And these are two flanges in facing each other. They are fixed together using some magnets, and you can remove the mobile flange in number two. And so you remove the whole coupling system, and you can put it back again against the fixed flange, and you will not have to sustain important loss of power or to redo your alignment. So this is useful for a user who needs to swap between free space mode or injected mode. frequently. Yes, to give you an idea about the dimensions of the L1C, the laser head is a little bit shorter. So we have two laser heads actually, depending on the mix of options that have been selected, earlier here by the customer. The outcome, we will integrate all these options into either of these two packages. So none of them is longer than 180 millimeters. Also, you should keep in mind that an extra probably 10 centimeters is required if you want to build an escape route for the patch cable. And there is a heatsink attached to this L1C laser head. And in the case where the acoustic modulator is chosen, then the external driver, the BTC AOM, is this size. So about 170 millimeters. 17 centimeters by 20 centimeters by 9 centimeters. Okay, L1C is used. So this is a typical setup that I built, imagined for an L1C with the MPA, the motorized power attenuator. I imagine that user drive the power using a computer, but it is also possible to do so using a signal generator or both. So what will be on the table would be a power supply, which we provide, an AC-DC converter, then a controller looking like a remote control with a key control to be compliant with the safety standard, and the L1C head that we described would be, as I imagine, on the table. Another possible layout for L1C OM would be the laser head here, and then the driver that we saw 2 slides ago, the BTC OM. The driver is fed by its power supply because it requires a little bit more power than just the laser head, and the user could apply its signal generator to the driver in order to modulate the optical output. This is what the user would be facing from the controller, from the computer. So this is our graphic user interface. Basically, the emission is controlled by the internal shutter. The laser cavity, the laser emission starts automatically, as soon as the emission key is turned on, and then the user can control the emission through the electromechanical shutter. Then here the power adjustment can, the power can be adjusted. And on the left-hand side, of the screen, the user can decide to enable or disable the modulations. So we provide two types of modulation. Digital modulation is two states, on or off, and analog modulation is about providing us optical power that is proportional to the input signal, to the amplitude of the input signal. The standard for standard operation implies that we linearize the output of the modulator against the input, which is not obvious if you know how an acousto-optic modulator reacts. We thought that it was better to linearize this, but the user is able to suppress the linearization by using this direct mode option. Would you have any questions so far? Anyone? You could just type them into the chat box. So further on, I would like to state that the L1C is compliant with the safety standards. So the IEC 60825, the most recent version, and the FDA 1040 10 and 1040-11. In concretely speaking, the L1C provides an emission key to the user on the remote control. There is an interlock circuit, so an interlock function that the user can connect to the circuit prepared in his or her equipment. And there is also a beam shutter that we have showed you about. And there are warning luminous, luminous warnings prior to the emissions, and of course the standard safety levels in use. So I would like to show this setup that I've been describing a few slides earlier. So this is what it could look like on your table. This is the L1C laser head with I put optical a delivery of the beam into an optical fiber. So this is expected to be sitting on the optical table. Yes, so I have a question here concerning the heat sink. So obviously my table was not an optical table, but if you fix the laser head to an optical table, a standard one, then you wouldn't have to use the heat sink. The heat sink is meant to allow the user to lay the optical head any place, and not just on a heat conductive support. And this is the remote control. So this is expected to be closer to the users near the computer, for example. And in the background is the BTC OM, where the modulation signal would be applied to, or the interlock circuit would be connected to, or we also provide this where the computer is supposed to be connected through either USB or Ethernet. And on the left-hand side is a connector with various connections that allow the user to select, to program some functions or to modulate also the beam. I have video for you to share, but so I will pause. Let me start the video and switch. So this is a measurement that we've been doing on a true system. Sorry. You can see the L1C laser head it's actually L1C plus A. This is the longer version available. It's standing on top of the heatsink, which is a motorized heatsink with the fan inside the blue housing. And it's been releasing its beam on the left-hand side of the screen. And on the right-hand side of the screen, you can see the AOM controller, the BTC AOM. So this is what states. You have the laser head. Inside is embedded 532 nanometer laser. The heatsink with active temperature stabilization is beneath, and the controller is on the right-hand side. So my colleagues were testing the linearity of the modulation, so the analog modulation. Oh no, sorry. This is a different modulation. So they are applying a square signal from 0 to 5 volts. This is with 1 kilohertz repetition rate using a simple BNC to SMB cable. And this is what they obtained. And we've zoomed from, from that screen. If we zoom looking at the rising front, you can see that the rise time is little less than 100 nanoseconds. And then my colleagues applied the triangle signal in order to test the linearity of the modulation. So you can see it's fairly linear, and this is the standard mode and not the direct emission mode. And so the linearity is over 2%, sorry, less than 2%, and the contrast between the highest level and the lowest level is 40 decibels. So I'll be back to my presentation. Okay. Yeah, so this was to show you how you could be measuring the actual rise time of the L1C. So such a short rise time is difficult to achieve using a standard DPSS laser, especially a laser with a single longitudinal mode. I wanted to show finally another application, which is a frequency stabilization using iodine transition. So the idea is to get further down into stabilizing this frequency of the green emission using atomic transition of iodine. The components that will be required for this is a 532 nanometer L1C source that we have discussed about, to which will be applied a wavelength selection and tuning, and also an AOM, a specific AOM with a control over the power carrier, so the radio frequency carrier that is powering the crystal of the modulator. And all this can be embedded into an L1C AOM. So if you take a standard LCX, so DPSS source from Oxus, the precision of the emission frequency from one start to the other one is actually less than 1 gigahertz, but let's say it's plus minus 1 gigahertz, because it's difficult for us to measure with this frequency with higher precision. Then Oxus is able to provide an option by which the user will be able to tune the frequency, the emission frequency further down than this, using, so this option allows the user, you see the dotted line in green is the user's set point, and the black line is the response of the, so this is the frequency of the signal. So this is something that we've measured using a Fabry-Perot interferometer in order to assess the variation of the frequency over time. And on top of this, if one used the RF carrier of the AOM, the modulator, with a specific driver that can control the RF, the carrier frequency down to less than 100 hertz, then doing so, the overall system can be used to control the frequency, emitted frequency, to less than 100 hertz, which is where the application, the iodine application can make sense. Okay, so we've reached the time. Thank you for your attention. Do not hesitate to leave me some questions or messages if you have any. I will leave some